second slide.
Yes, yes, yes.
Great.
Okay, so let us start this final talk in this workshop. So the speaker is Yoshifumi Nakata from University of Tokyo, and he will tell us about decoding the Hayden Preskill protocol from classical to quantum information. Please start.
Okay, thank you very much for the introduction, and thanks everybody for coming. I'm Yoshifumi from the University of Tokyo, and in this talk, I'm going to talk about how to decode the so-called Hayden Preskill protocol. Okay, so this is an outline of this talk. I would like to start with a brief introduction of the Hayden Preskill protocol, and I will also overview the result obtained by the in the original paper. And this Hayden Preskill protocol is sort of information theoretic toy model of the information paradox of quantum black holes. And in this talk, we are going to study this protocol from the viewpoint of quantum information. And I think it's better to say that I'm basically working on quantum information. So I have little knowledge about high energy physics. So I cannot talk about ADS-CFT or holography or something like that. And this talk is mostly from quantum information perspective. But I hope you enjoy this talk. And then the main result of this talk is we provide a new decoder for the protocol. And we call that decoder classical to quantum decoder, because this is kind of interesting decoder. We first decode classical information in the protocol, and then we lift it up to the decoder for quantum information. And for this reason, we just call the new decoder classical to quantum decoder. And then thanks to this decoder, it's sufficient to consider only how to decode classical information in the protocol. So in the third part, I will explain how to decode classical information. And finally, I will apply these two results into the Hayden Preskill protocol and show you how to decode both classical and quantum information in this protocol. And I will conclude my talk. And maybe this talk is a little bit technical, maybe. So I would like to give you two take-home messages in this slide. And the first message is, I have already told you, but if you know how to decode classical information in general, you can decode quantum information as well. So this is the first message. And the second message is about the sufficient condition for the information recovery. And we find that if we use a particular type of decoder, purity of an output state of the noisy channel, or like in the radiation in Hayden Preskill protocol, is very important. So purity is a kind of key factor when we talk about the information recovery. So this is the second message. Okay, so anyway, this is the plan of this talk. And let me start with a brief introduction of the protocol. So again, this protocol is kind of information theoretic toy model to study the information paradox of black holes. So from my viewpoint, the information paradox is something like this. So we start with the whole universe, which is prepared in a pure state. And we also assume that black hole is there and it is in a pure state, let's say. And this pure state psi carries some information of the black hole. And we just let the whole universe undergo some unitary time evolution. And we believe quantum mechanics is correct. And then, believing the calculation of field theory as well, we have Hawking radiation. So eventually, the black hole evaporates. And we have the Hawking radiation, which looks locally thermal in the end of the day. But this Hawking radiation looks locally thermal, but assuming the quantum mechanics, we should be able to recover the information of the black hole from this Hawking radiation, right? Because we assume that the dynamics is unitary, which is reversible. So the question here is to recover the information of the black hole, how much radiation do we really have to collect? So this is a sort of main question in this protocol. And of course, as I said, the unitary dynamics is reversible. So if we collect all the Hawking radiation after the black hole is completely evaporated, then we should be able to successfully recover the original information of psi, because we just apply U inverse. But what we have learned from this protocol is that if the black hole is scrambling, then this information recovery is possible from much less radiation. So this is a kind of surprising result that they have obtained. And now let's move on to this protocol. Yeah. So this is a scheme of the Hayden Preskill protocol, and this is a qubit model of the information paradox. So we start from the initial state of the black hole, which is in a mixed state in general, Gz of n qubits. So this part is an initial black hole composed of n qubits. And we assume that this black hole is purified by the past radiation. So this is a Hawking radiation emitted earlier than this time, sometime. And we assume that this is a purification. So the initial state between the black hole and the past radiation is in a pure state, which we denote by ket Gz. So this is an initial situation. And we throw a k-qubit quantum information A into the black hole. Okay, so we just, for example, prepare an unknown pure state psi and throw it into the black hole. And after the quantum information source is thrown into the black hole, the whole black hole undergoes some unitary time evolution, which we often assume scrambling. And after this unitary dynamics, we split the whole black hole into two random subsystems. One can be called the remaining black hole, and the other represents the new Hawking radiation. And in this talk, we assume that this new Hawking radiation is composed of L qubits. So L is an important variable in this protocol. And finally, somebody collects both the past and new radiation from the black hole, and we try to decode the original quantum information of A. Or we could say we just try to decode or recover this initial state of the information source A. So this is a whole scenario of the protocol. And as I said, we were interested in how much radiation do we have to collect to succeed the decoding of the quantum information source. So the question is, in order to successfully decode the k-qubit quantum information, how large should L be? L is the number of qubits in the new radiation. Good. And when we talk about information recovery, of course, we should first define what is a recovery error. So let me first explain how we typically define the recovery error. And we just follow the convention of quantum information theory. So we introduce a reference system R and prepare k-EPR pairs between A and R. So instead of throwing unknown pure state psi, we just introduce a new system, reference system, and we just prepare k-EPR pairs between A and R. And if we succeed to recover this k-EPR pairs in the end of the day after we apply the decoding operation, then we say we succeeded the decoding quantum information. So this is a very typical definition of the recovery error. And based on this, we define the recovery error in this way. So this is delta Q. Q denotes represent the quantum information. So this is error for quantum information and defined by this simple distance between two states. So the first state, low fin, is a state of the output system of the decoder and the reference. So this is what we obtain at the end of the day. And the phi AR is just k-EPR pairs. And as I said, if these two are close enough, then we say we succeeded the recovery operation. So this is the error. And here we have parameter one, the normalization factor 1/2. But because of this normalization, this recovery error is normalized so that it is always between 0 and 1. And 0 is good and 1 is bad. Good. So this is the recovery error. And in the original paper back in 2007, I think, so they proved this inequality. If the dynamics of the black hole is scrambling, then we take the average over the all scrambling dynamics, or we could say the average over all hard random unitary of this recovery error. Then it is bounded from above by this. So this is basically just an exponential function. And in the exponent, we have some threshold number L minus L. So L is again the number of qubits in the new radiation. So if the number of radiation qubits in the radiation exceeds this threshold value, then the error decreases exponentially quickly, and we succeed decoding quantum information. And this threshold value is given by this one. So this is k plus n minus h2 over 2. And k is the number of k EPR pairs that we throw into the black hole. And n is the size of the initial black hole. And h2 of Gauzy, so this is the so-called collision entropy of the initial black hole being. So the definition is simply, we take the trace Gauzy squared and we take a minus log of that. And Gauzy is an initial state of this initial the black hole of n qubits. Okay, so this Gauzy is not this pure state. So we just trace over the past radiation and we obtain the state Gauzy, which is in general mixed state. So what we can learn from this statement is that the L to recover the k-qubit information, L should be larger than the threshold value. And also this threshold value is determined by the entropy of the initial black hole. So this is the kind of message we obtain from this theorem. And now, so this is very convenient. So we can just plug in some special cases, for example. The first example is if the black hole is initially in the pure state. So we could say maybe the initial black hole is at temperature 0. And in that case, there's no past radiation and it's just pure state. So the entropy of the pure state is of course 0. So in that case, the threshold number is just k plus n over 2. So if the black hole evaporates a little more than like half, this n over 2 is half. So then we can recover the k-qubit quantum information. So this is a case when the black hole is pure initially. And another interesting example is when the initial black hole is completely mixed state, or we could say the infinite temperature maybe. And in that case, because this is a completely mixed state, this entropy is maximum. So actually we have these two terms cancel each other and the threshold value becomes only k. So this means that if the initial black hole is completely mixed and if the dynamics is scrambling, then we just have to collect only k qubits of new radiation to decode the original k qubit information. So there is no term n. So no matter how large the initial black hole is, if we throw k qubit information and if we get k new radiation, we can infer what information was thrown into the black hole. And this is kind of interesting because black hole is not black at all. So if the black hole is scrambling, then it's kind of mirror of information. So this is what stated in this paper. Okay, so this is a brief overview of the Hayden Preskill protocol. And after this proposal, there are several extensions of the protocol. For example, in these papers, they argued what happens if this dynamics of the black hole is energy conserving. So in the original analysis, we just assume that the dynamics of the black hole is completely scrambling. So it mixes everything up. So energy is not conserved in the original proposal. But in physics, maybe it's more sort of natural if we consider the dynamics that conserves energy. So they take this energy conservation into the account and they investigated the protocol. And I was also interested in this kind of argument. And in the end of the day, I wrote one paper and it states that if there is an energy conservation, then it results in a non-trivial delay of information leakage, meaning that to recover quantum information, we have to collect more radiation. And that is what we mean by delay of information leakage. And actually, this delay can be characterized by the heat capacity of the black hole. So this is the delay of the information leakage, and it's proportional to this quantity. E is the energy of the initial black hole, S is the entropy of the initial black hole, and CV is the heat capacity. So this is a kind of interesting relation that connects some information theoretic quantity, left side, and right-hand side, we have lots of physical quantities. So I think this is sort of interesting. Well, of course, we have assumed many things, but this is one implication when the dynamics is energy conserving. And there's another direction of extending the protocol. So these guys also addressed how to explicitly construct decoders. So in the original analysis, the decoder of this protocol was very implicit because the original argument was based on so-called decoupling argument, and decoder is sort of implicit in that argument. So these guys showed constructed the decoder explicitly. And for example, in this paper, Benny and Kitaev provided the kind of teleportation type decoder. And they found that this decoder is closely related to out-of-time ordered correlators. So this is, I think, very interesting because, again, decoder is a matter of information theory, but OTOC is a matter of physics, right? So by considering the decoders, we can connect information and physics to some extent. And also recently, Pennington and other people found some relation between PETS recovery map, PETS decoders, and space-time geometry. So this is also very interesting, at least to me. So what we can learn from these two is constructions of decoders might bridge the information theoretic protocol to some quantities in physics, such as OTOCs or some space-time geometry and so on. So in this talk, I would like to follow this line of the analysis, and I would like to provide a new decoder of the protocol. Okay, so this is a motivation. Good. So let me first give you a short summary of our result. So the first result in this talk is we provide a new decoder for the Hayden Preskill protocol. And as I said, we call the new decoder a classical to quantum decoder because we first decode classical information and upgrade it to the quantum version. And then we provide a sufficient condition for the information recovery in terms of the purity of the output state. Or in this protocol, what is important is a kind of purity of the state in these radiations. Okay, so this is the second result. And here I should emphasize that, I was saying these are decoders and sufficient conditions for the Hayden Preskill protocol, but actually these two results hold in any protocol, and we don't have to assume scrambling as well. So maybe these two are useful to study non-scrambling black holes, or maybe it's also useful to study just information recovery in the from the noisy quantum channel. So maybe this is also interesting in quantum information as well. And finally, we apply these two techniques to the Hayden Preskill protocol, and we show how to decode classical and quantum information. And short summary of this is given by this simple table. So we just assume that the black hole is scrambling dynamics, and we investigate the recovery error for quantum information and also classical information. And in the original paper, it's already obtained that the recovery error for quantum information is given by this. But of course, they didn't address classical information. And in this, by using our technique or our decoder, we succeeded to obtain a slightly better result for the quantum information. Well, I don't think this is very important, but the difference is here is 1/2, but we don't have 1/2 here. So the scaling is better. But again, this is not very important at all. But also we obtained the recovery error for classical information. And this is just given in a kind of similar form. But instead of 2 in the basis, we have 4 here. And but the exponent is exactly the same. That is what we have found. So from this result, maybe we can say that if the black hole dynamics is scrambling, then both classical and quantum information is emitted simultaneously. So actually the difference between classical and quantum information in this protocol is not that much. So they are available when the number of qubits in the new radiation exceeds this threshold value. So this is one kind of conclusion from our calculation. But maybe the difference between classical classical and quantum information is just how quickly the error decreases. So the difference is if this is 2 or this part is 4. So this is the only difference between classical and quantum. Okay, so this is our last result. And only this part, we assume that the dynamics is scrambling. Okay, so this is the kind of short summary of our result. And yeah, now I'm going to explain result 1, 2, and 3, just step one by one. Okay, good. So let me tell you how we construct a decoder for the protocol. Okay, yes, so in the construction of a classical to quantum decoder, as I said, we don't have to stick to the Hayden Preskill protocol. So in this part of the talk, I would like to consider a general protocol, which is in general given by this form. So we prepare k-EPR pairs initially, and we apply some CPTP map T, and this CPTP map changes this quantum information system A to the output system C. Okay, and then we apply a decoder which recovers the system A from C, and then we try to obtain the k-EPR pairs between A and reference system R. This is a general protocol. And of course, this protocol, HP protocol, is a special case of this because we can just identify this output system C as a new and past radiations. Right? So you can just see this in this figure. So in this Hayden Preskill protocol, so this input here is of course the input here, right? And then the output C here corresponds to the new and past radiation. And this CPTP map T is all the others in the green box. So of course, in this case, we've prepared the black hole initial state, but that is also a part of the this CPTP map. Okay. So with this identification, this is the general protocol is a proper kind of generalization of this protocol. Perhaps you can understand. Okay, so and based on this general protocol, I'm now going to explain how we construct the C2Q decoder. By the way, I just called this classical to quantum decoder like C2Q. It's just a simple abbreviation. And the basic idea of this decoder is that if we can decode classical information defined in two complementary bases, like Pauli X and Pauli Z bases, then we can actually decode quantum information as well. So following this basic thing, we are going to construct this C2Q decoder. So now let me explain what is classical information, or how we can define recovery error for classical information. So to define this, let JW be the Pauli W basis, where W is X or Z. So we have Pauli X or Pauli Z basis. And then instead of input the maximally entangled state or k-EPR pairs, we just input one of the states in the basis. So for example, when we choose Z basis, we just choose like a JZ randomly, and J is K bit. Okay. Then after this CPT map, we try to recover this J state. So it's a very simple protocol, right? And this is what we call the recovery of classical information. And based on this, we can just define the recovery error for W classical information by this equation. So this one, JW is the initial state. In this case, JZ, right? And then this term is we apply the CPTP map T and we apply decoder. So we are just trying to decode or recover this J state by applying decoder. And 1/2 is just normalization. And after that, we take the average of this quantity over the all choices, uniform choices of J. So this is kind of average distance when the input is one of the basis state. And we define the recovery error for W classical information in this way. Okay. Good. So now suppose that we have P of M. So this is quantum measurement. So we just perform some measurement on MW to decode W classical information. Because the information is classical, we perform some measurement, and if the measurement outcome is, for example, J, we just infer that the information is J or something like this. So we can represent the decoder for classical information in terms of measurement. So let's suppose that we have a kind of P of M, X and MZ. And then assume that the recovery error for W classical information when we use this quantum measurement is given by delta X and delta Z. And what we are going to claim is that from these P of M's for X classical and Z classical information, we can construct a good decoder for quantum information. And the basic idea for this is we combine coherent measurement and error correction by MZ. So let me explain what I mean by coherent measurement. This is not a usual term, but I want to call this coherent measurement because we are going to apply this isometry. So this is an isometry from the output state C to C and A. So we just attach a new ancillary system or something, and we call that ancillary system A. Okay. So we just extend the Hilbert space. And this isometry is given by this form. And MXJ is the P of M element for X classical information. And if the measurement result is J, we kind of coherently generate a J state in the ancillary system. So this is an isometry. So it's a kind of feasible dynamics in quantum mechanics. And to construct a quantum decoder, we combine this isometry with just an error correction. So actually the C2Q decoder is given by this form. So the input is C, and then we apply this isometry. So the output is now C and A. And then in the error correction part, we perform measurement of the C system in the Pauli Z basis. The P of M for Z classical information. And depending on the outcome of this measurement, we apply some error correction onto this system A. And this error correction is just application of Pauli operators. So it's a very simple operation. And finally, the output system is only A. And the system C is already dead because this is measured. Okay. So as in total, this map, coherent measurement plus error correcting part has an input C and output A. So this is what we call the unclassical to quantum decoder. And what we can show about this decoder is the following inequality. So this is a recovery error for quantum information when we use a C2Q decoder. And this is bounded from above by recovery errors for X and Z classical informations given by this P of M measurement. So this is our first main result. And yeah, you can see that if both recovery errors for classical informations are small, then the quantum information, recovery error for quantum information should be also small, right? So from this inequality, we can say that if we know good P of M's for X and Z classical information, then we can construct a decoder for quantum information. That works very well as well, right? So this is kind of our first result. And thanks to this decoder, now we can forget about quantum, and we can just focus on classical information. So in the next part, I will explain how to decode classical information. So now we go back to the classical world. We don't care about quantum anymore. Okay, yeah, so let me, or do you have any question? Is that okay so far? Is okay? Okay, so let me continue. So next I will explain how to decode classical information. So yeah, again, wrapping up the C2Q decoder, because of this technique, we can now focus on P of M's for decoding classical information. So this is the original protocol, but if we use a C2Q decoder, we can sort of classicalize this protocol to this one. So this is much simpler because there's no EPR pairs in this classicalized protocol. We just input one of the basis, Pauli Z basis state, and we try to recover it. So it's a very simple protocol now. And decoding of classical information has long history in quantum information science, and it's already known how to decode classical information like almost 20 or more than 20 years ago. So in their very good paper by Horevo, Schumacher, and Westmoreland, and they showed how to decode classical information. So what we are going to do now is we steal the ideas from these two papers, and we construct a decoder or POVMs for classical measurement. But if you are from quantum information community, maybe you know the answer. We are going to use pretty good measurement. So yeah, now let me explain what is the pretty good measurement. This is known as a good decoder for classical information in general. So what is this? So here we have a classical protocol, right? Then we are going to construct a pretty good measurement for this protocol. And to this end, we have to first compute this state tau j. So this is just an output state of the CPTP map when the initial state is ket j state. Okay, so this is simple state tau j. And from this tau j, we first compute the support of this state and construct a projector onto that support. And we call this projector pi j. And from this projector, we construct a POVM in this way. So this is what we call pretty good measurement. So this is basically, we sandwich pi j with pi to the power minus 1/2. Right? And pi is given by just a summation of pi j over all j. And it's kind of straightforward to check that this is a correct, this is a feasible quantum measurement. So you can easily check that this is POVM. And yeah, it is known that if we use this pretty good measurement, POVM, in this decoding process, we can basically decode the classical information. Okay. So we are going to use this pretty good measurement. And now I can give you a sufficient condition for the information recovery. But to explain the sufficient condition, let me first introduce one more notation related to this state, tau j. So we are going to use this notation, lambda min of tau j, which is just a minimum non-zero eigenvalue of this state, tau j. Okay. And then we take the minimization over this lambda min tau j over the whole j. So j is k qubit. So we have 2 to the k choices. And we just take the minimum over this. And that is what we denote by lambda min w. And the w is z or x. So we have lambda min z and lambda min x as well. And to define lambda min x, we just change this basis state to the Pauli x basis. So we have two things. And using this notation, we can give you the upper bound of the recovery error for W classical information, which is given by this. So here we have lambda min of W, and we also have something, two more terms. But the first term, this one is 2 to the power of k. Oh, by the way, k is of this k qubit information, and times some purity of the output state when the initial state is identity over d. So this is a completely mixed state. So the first term is given by the purity of this output system when the initial state is completely mixed. Okay. So this is very important quantity in the upper bound. And the second term is this is just an average purity of the output state when the initial state is j, one of the Pauli z or Pauli x bases. Yeah. So this is also related to the purity. And you may find this is a little bit complicated because we have two purities. But after some very easy calculus, we can actually bound this again by in terms of lambda min and this purity. And DC is essentially kind of the dimension of this output system. Well, it's slightly different, but it's essentially the same as the dimension of the output system. So now we have an upper bound in terms of one purity and this lambda min of W. Right? So one thing I have to say at this point is that this is an error for WX and WZ errors information. So this is basis dependent, right? But actually the upper bound is dependent on the basis, choice of the basis, only in terms of lambda mean W, right? So the basis dependence appears in the upper bound in terms of this lambda mean W. So this is one node. But actually, we find that we calculated this quantity for several cases, and it seems that when the information is decodable, actually this lambda mean W is approximately given by 1 over dimension of the output system. Well, this is not a proof, this is just our speculation, but this is at least true for several instances. So when this is the case, we can also further simplify the upper bound. So we just substitute this quantity to here and there. And the upper bound is now simply given by 2 to the power k times dimension of the output system and purity of this state and -1. So it's such a very simple expression of the upper bound of the recovery error for classical information. So
Can I ask a question?
yes, please.
So this is for, you're taking optimizing up against this POVM?
No. We
you
use a pretty good measurement. Yeah, we just fixed the POVM as a pretty good measurement. And this is an error if we use this POVM.
I see.
Yeah. So there's no optimization.
Also MW here?
MW.
So
oh, MW.
Argument of delta W.
This one? Oh, so this is the POVM, the pretty good measurement.
That's
yeah. So here, yeah, this one.
So also, but this pretty good measurement is the best choice, or about this delta W?
It's close to optimal. That is what we believe, as far as I understand. But I don't know if it's really the best or not. But it's really good.
I see.
That's why we call it pretty good measurement. Yeah. Yeah, thank you for the question. Okay, yes, so now we have an upper bound of the recovery error for classical information, and it tells us that if we are able to compute the purity of this state, then we know the upper bound of the recovery error. And if it is small, then we can recover the classical information very well. And thanks to the C2Q decoder, if we succeed to decode classical information well, then we can also decode quantum information as well. So this is really the sufficient condition for the information recovery. So this is, I believe, important. So I will rephrase: information recovery is characterized mainly by purity of this state. Good. So this is our second result. And finally, yes, I will use these two techniques to decode the information in the Hayden Preskill protocol.
Can I ask you a question?
Yeah, please.
Yeah, on this slide, what is your definition of decodable?
Decodable. Oh, that's a good question. So this is just speculation. So there's no definition of decodable. But I would say that if the error is kind of small, can be small. So, well, yeah, this is not very logical, I would say.
So
yeah.
Which cases did you try?
Good question. I just assume that this CPTP map is consists of like scrambling dynamics plus some noisy map. Yeah. So yeah, this is very heuristic, and I think there is an exceptional case, but yeah, as far as I computed, assuming the scrambling dynamics, then this seems to hold.
I see. Thank you.
Great. Okay, so now let me explain how to use the C2Q decoder with pretty good measurement to decode the Hayden Preskill protocol. So we come back to this protocol, right? Yes, and we are going to use a C2Q decoder to decode this protocol. And the decoder is this part. So of course, the decoder in this protocol has input, new radiation and past radiation. And the output is system A. And because we are going to use C2Q, we first assume that we know good POVMs for X and Z classical informations. Yeah. So this is an assumption of the C2Q decoder. And we just perform coherent measurement and error correction to obtain the system A. Okay. So this is what we are going to use. And then for these POVMs for classical informations, we are going to use pretty good measurements. So yeah, these MX and MZ from now on, they are just pretty good measurement on two radiations, past and new radiation for X and Z classical information. So just to make everything more concrete, I'm again going to explain how we can construct PGMs in this protocol. So yeah, in the original protocol, we have to input EPR pairs. But here, to construct PGMs, we input one of the Pauli, for example, Pauli G basis state. And then we obtain some quantum state acting on the new and past radiation. So GZ J is a state of on the radiation. And from this state, we construct a projector onto the support of that state. This is pi j. And by sandwiching this pi j with the summation, and then we can construct a pretty good measurement for Z classical information. Okay. And similarly, we can also construct a pretty good measurement for X if we replace this initial state to the one of the basis state of Pauli X. So this is how we construct PGMs in this protocol. Okay, yeah. Then, yeah, to compute the actual recovery error, when we use this C2Q decoder, we first should record our first main result, which states that the recovery error for quantum information is bounded from above by recovery errors for classical informations. And to compute these things, let us now assume that the dynamics of the black hole is scrambling. And if the dynamics is scrambling, maybe it's easy to imagine there's no difference between X and Z classical information. Because even if we input Pauli X basis or Pauli G basis, if this dynamics is scrambling, doesn't make any difference, right? So on average, the X and Z information are the same in this if the dynamics is scrambling. So meaning that if we take the average of the errors over the scrambling dynamics or how random unitary, then yeah, this delta X and delta Z becomes exactly the same. So we have an upper bound of this, and delta CL is recovery error for classical information. So this is already kind of interesting because the error for quantum information is bounded from above by square root of the error of classical information. And we also have the inequality on in the other side. This is a trivial relation that stating that classical information error is always smaller than the error for quantum information. Well, this is trivial because classical information is always easier to decode than quantum information. So actually, we can sandwich the error for quantum information by errors of the error of classical information. One side is just square delta CL, and the other side is square root of that. So meaning that by assuming the scrambling dynamics, we can conclude that quantum information is recoverable if and only if classical information is. And this means that the black hole with scrambling dynamics releases both quantum and classical information exactly at the same time. Okay, so now we have these two inequalities, and what we have to do from now is we have to compute this delta CL. But this is also sort of already done if we use the second our second result, because the recovery error for classical information is given by this one. So basically, essentially, this is dominated by the lambda mean, the minimum non-zero eigenvalue of these states, and the purity of this state, the purity of this state. And again, we use the assumption that the dynamics is scrambling. then we can prove that this minimum non-zero eigenvalue is given by some quantity with high probability. And by substituting that value to this lambda mean, we obtain an upper bound in this form with high probability. And again, this is just characterized by the purity of the output state when the initial state or input state is a completely mixed state in system A. So this is a very convenient upper bound, we believe. So this is what I have explained. And finally, to compute this average, we just take the average of this over the Haar random unitary, and we can show that this average error for classical information is given by basically 4 to the power of the L threshold minus L. And L threshold is the usual one, K plus N minus entropy of the initial black hole over 2. So good. So this is a kind of one conclusion from our calculus. And then by plugging in this value into this inequality, we obtain the recovery error for quantum information. But basically, it's just a square root of classical error. So 4 becomes 2, and that's it. So this is our calculation. These two things have several implications, maybe small implications. Again, I would like to emphasize that there's no big difference between classical and quantum information in this protocol, because both can be recovered from the radiations when the number of qubits in the new radiation exceeds this threshold number. So this means simultaneous emission of C and Q information. And the difference is again the basis. So if we have the same amount of new radiation, then the classical error information can be recovered more precisely than the quantum information. So that is the only difference between classical and quantum. And also, well, this is not again important, but I will slightly improve the original result. So this is basically everything that we have proved, but let me just add one more comment. So we assumed scrambling dynamics only in the last calculation. So the C2Q decoder with pretty good measurement, as well as the formula for recovery error of classical information, works for any dynamics of black holes. Or in general, if we have any noisy quantum channel, these two things work as well. And then we argued that the recovery errors are mostly characterized by the purity of the state when the input is the output state of the channel when the input is a completely mixed state. So we believe that these two things can be applied to maybe different scenario of black holes or noisy quantum channels. So this is kind of one comment. Good. Okay, so we are almost done. So let me conclude my talk. So in this talk, we studied the Hayden Preskill protocol as a toy model of a quantum black hole. And I explained that this protocol is a kind of very nice framework because it provides lots of insight that may bridge information to physics. For example, we can connect information leakage problem with heat capacity, OTOC, space-time geometry, etc., etc. And that is a reason why I was fascinated by this protocol. And then we had 3 results. The first result is the classical to quantum decoder for quantum information. And this is kind of interesting because we start from classical regime and then we update it to quantum regime. We also provide a sufficient condition for the information recovery in terms of purity. But please note that this sufficient condition is a condition when we use pretty good measurement. So if you use another measurement or another decoder, maybe we could have another condition for the information recovery. And these 2 results work for general protocols. But finally, we applied these 2 to the Hayden Preskill, and we showed how to decode classical and quantum information. Maybe one important message is there is no big difference between classical and quantum. Okay, so there are several open questions. So let me give you 3 open questions, and then I will conclude this talk. So the first open question is, in this talk, we provided the C2Q decoder with pgms, but we didn't talk about if we can efficiently implement these decoders. So, and actually, the pretty good measurement is maybe difficult to implement efficiently. So one good question is it possible to efficiently construct these decoders? But these days, one good technique called block encoding was proposed. So if we use this technique of block encoding, we can actually implement a pretty good measurement. Well, it's not guaranteed if it is efficient or not, but there's a way to implement pretty good measurement. So maybe you can use this technique to check if our C2Q decoder is efficient or not. So this is an interesting open question that I have to address. And another open question is that, yeah, a relation between our decoder and the PET's recovery map. Indeed, this pretty good measurement is a special case of the PET's recovery map. So I wouldn't be surprised even if in the end of the day, these two decoders are the same, or our decoder is a special case of the PET's recovery map. But at least at this point, I cannot see the direct connection between these two. So I'm very interested about the relation between these two decoders. And finally, this is what I cannot do by myself, but I'm also a little bit interested about the space-time geometrical interpretation of purity. So as I said, the sufficient condition for information recovery is given by the purity. And we just fix the input state as a completely mixed state. And if we know the purity of the radiations, then we get some criteria for information recovery. And the purity might have a good interpretation in terms of space-time geometry. Well, I'm not pretty sure, but if it is, then I think that is very interesting because we can interpret our decoder in terms of like the world of space-time geometry. But apparently I cannot do that by myself. So if some of you are interested, I'm very happy to work with you. Okay, so these are 3 open questions. And with this, I would like to conclude my talk. Thank you very much for your attention.
Thank you very much. Wonderful talk. It's time for questions. Any question? Patrick?
Yeah, I had a few questions. So maybe one of them, just to get started. This smallest eigenvalue quantity that's playing a big role in your bound.
Exactly, yes.
That's a very strange thing to appear. Like from the point of view of one-shot information theory, what usually appears as largest eigenvalues or ranks or purities, like
right.
smooth, but a smallest eigenvalue is bizarre. And so I was wondering if you could comment on that and whether there's any relationship between the bounds that you get and the one-shot information theory.
Yeah, thank you for a great question. And I actually suspect that this minimum eigenvalue appears for just technical reason. So just for proof. So I hope to get rid of this quantity, but I can't at this point. So yeah, right. And this is not very essential in this analysis, I believe. And also from the viewpoint of smoothing technique or something, we can always introduce some smoothing technique to cut off very small eigenvalues, right? So if we introduce some smoothing technique, maybe this lambda mean can be replaced with an arbitrary constant epsilon or something. That's my comment, but yeah, I should do that more further analysis on this.
Okay. I could ask you more questions, but I'll wait until others have asked if they have some. Thank you.
Thanks. But if there is no question, you can continue maybe.
Okay, well, so I guess another question was whether you can use your method for a general channel to show that the coherent information rate is achievable. Does this give a proof of that statement?
Yeah, definitely we can use our decoder for like coherent information things. But that is kind of my next project. So I don't have much insight yet. Yeah, okay. But definitely it's we can use it. Yes.
And then a last question, you didn't speak about this, but you mentioned your earlier paper at the beginning of your talk, where you had this delay that was proportional to the energy times the square root of the heat capacity divided by entropy.
Yeah.
I was wondering, have you had a chance, like there are these recent papers over the past couple of years about actually decoding Hawking radiation, and they can calculate when they expect that to be able to happen in holographic scenarios. Do you know if this delay that you predict is consistent with the calculations that people do there?
Oh, sorry, I don't know. Sorry, I didn't follow that literature from the viewpoint of holography. So maybe, yeah. Yeah, the quick answer is I don't know. But yeah, it's a good comment. I think I should definitely check. But at this point, yeah, sorry, I don't have any comment on that.
Okay.
But I will
All
check.
right,
Yeah, thank you very much.
Yeah. Oh, and I maybe just one last comment. You asked about interpretation of the purity. Several years ago, and there's been follow-up, Shi Dong gave a holographic prescription for calculating Renyi entropies.
Oh.
Yeah, a generalization of the Ryu-Takiyanaki formula. And so if you look up Shi Dong and Renyi entropy holographically, you'll find what the prescription is for
okay,
going after that.
Shi Dong.
Yeah.
And
can
you give me
XI? I'll put it in the chat actually.
Oh yeah, that's great.
Yeah.
Thank you very much. I will check.
Yeah. Thank you for the nice talk.
Yeah, thank you very much for great comments and questions.
Okay, so any other questions? Yeah, I'm curious about this new decoder, C classical to quantum decoder. So do you think this has some implication to have some explicit map, like Hertz map?
Oh,
which we can actually use in string theory or some maybe quantum many body systems.
Yeah. Do I understand
some
correctly?
kind of formula which we can calculate. Sorry, I'm very.
Yeah. Yes. That is related to my second and third open questions, I guess. So first of all, if you're curious about the relation between our decoder and Hertz map, then we don't know the answer yet. But we hope that, at least I hope that, for example, the information recovery is characterized by this quantity. Yeah. So if you have a way to compute this quantity in field theory or like holographic context, then there might be a good kind of interpretation of our decoder. So that is what I'm most curious right now. And also, again, this state is very simple state. So did I write somewhere? I think. Oh yeah, I wrote it here. So this is a kind of the initial black hole. And we are curious about the state in the radiations when the input of the A system is a completely mixed state. So infinite temperature state. So if we know how infinite temperature state evolves after the this black hole dynamics, then we can basically obtain this purity. So maybe I can ask you, can you compute this in field theory or holography or something?
As Patrick mentioned, so anyway, in holography, we can calculate this quantity as a partition function because it's trace rho square. Rho is reduced density matrix, and it's a bit complicated, but it's kind of some partition function. And we have some gravity dual by kind of gluing geometry. And one way to do it is to introduce some cosmic extreme in the spacetime. That is G-Ton, I think, paper. This Patrick actually just quoted in this chat. It's a little bit more complicated than standard von Neumann entropy, but in principle, we can calculate. But in complicated geometry, it's quite. Azuma-san has a question.
Yes, thank you very much for a nice talk. And I have one question. Like your formula is close to the QKD in the sense that as long as the classical error is very small enough, then we can decode. And in this sense, that can we propose some experiment to check whether such a classical error is small enough by considering the specific dynamics of the black hole. Like a QKD, in the QKD, we confirm the error is small enough to just sending classical, sampling, right? Taking sampling. And do you have any idea to combine with your idea with such a sampling? In such a case, we can omit the assumption about the dynamics.
Scrambling. Yeah, maybe that's possible. Yeah, you are right. We are basically using the same technique as quantum key distribution, because this protocol is originally proposed by Masato Kawase. He's my boss, and he's an expert of QKD. And so I haven't thought about that scenario, but it should be possible, I guess. But I would say that's an interesting question, but I'm not an expert of QKD, so maybe I should learn a little bit more about that. But again, it should be possible, and if you are interested, we can do together.
Yeah, in such a case, we can say that unconditional decodable black hole or something like that.
Yeah, something like that. Sounds great.
Okay.
Yeah, good comment.
Thank you very much.
Thanks. Yeah.
Okay, so it's good time, I think, to close this meeting. So I just send all of you about this link to special chat. If you have a time, please join us in some online coffee break. And otherwise, we'd like to close this meeting. So let us thank all the speakers of this workshop for excellent talks. Thank you very much. And also all participants for coming to this online workshop. And we hope to continue this kind of workshop activity in next year and each year. And but hopefully we can have some more physical meeting. Also, collaboration. Thank you very much. Patrick, thank you very much for wonderful talk coming to workshop. So we move to this online coffee break in this special chat.